Hello and welcome to CS300 Introduction to Algorithms. I'm delighted to see so many of you registered and participating in this lecture, and I promise you, you won't regret it. You will get an entirely new perspective on algorithms far beyond the traditional approach as a collection and a method. Namely, will emphasize the logical perspective, and particularly the model theoretic view on algorithms. If you don't know or like model theory, don't worry at all. You will get a taste of it on the side, and you still get all the knowledge and insight that you know from this standard topic, which is provided at many lectures and many universities. So to start right away, let's start with an overview here, and what you see here. Just a second. Would go. Yes. So let's start with a little bit of administrative and formal matters. This course is heavily based on the book Corbin-Legerson Rivest and latest edition, including Stein, Introduction to Algorithms. If you have this book, you're happy. If you don't have this book, you might want to purchase it as a side to this course. Also, Donald Knuth, The Art of Computer Programming, 5 volumes, is still nowadays up to date and highly relevant to this course. Then there's Zipser, Introduction to the Theory of Computation. So to start right away with an overview. So this course begins with a motivation. We're already almost started with that. Then the next chapter will be about searching, following the Donald Knuth structures. Then sorting and sorting. Chapter 4 is about data, which is where the model theoretic and logical perspective really kicks in. Then we talk about graphs and graph algorithms in chapter 5. Chapter 6 is about strings, string problems and string algorithm. And we conclude with chapter 7 on algorithm paradigms. So that's the overview of the course, which will take us until roughly December. Yeah, the syllabus for the current chapter 1, introduction and motivation, we'll talk a little bit about computational problems and their algorithmic solutions, and in particular something that I'd like to call the virtues of computer science, as opposed to, for example, coding, programming, and other approaches such as common in, for example, in electrical engineering. The emphasis here is scientific, foundational aspects, such as emphasis on problem specification, semantics of instructions and programming, algorithm design as opposed to coding, algorithm efficiency analysis, algorithm optimality. This is something that only science can to prove that something is optimal, something is better, is infeasible. We'll illustrate this first with a simple example of repeated squaring, and then with more involved examples, and in particular the effect of having different operational primitives at our hand. So if we, whether we are allowed to do exponentiation or not, makes a tremendous difference on the which algorithms which one is considered an algorithm and which one is not, and what is an optimal algorithm and which one is not. And we will illustrate this by a sequence of 5 algorithms, all revolving around the same problem of computing Fibonacci numbers, but with better and better, more and more efficient algorithms, which on the other hand also use more and more powerful primitives. As that's the point here, demonstrating the effect of various primitives. Then we'll have a brief recap on some selected aspects of discrete mathematics, such as recurrences and the master theorem for solving recurrences asymptotically. And then we'll proceed to the second major example of motivating and illustrating the effect of different algorithms, namely polynomial multiplication. In this case, we will look at another sequence of algorithms: long multiplication, Karatsuba multiplication, two multiplication, and Cook multiplication from the PhD thesis of Stephen Cook, providing an entire family of algorithms with increasing asymptotic efficiency, all for the problem of polynomial multiplication. And then we'll have a final look at matrix multiplication, which also kicked off a similar sequence, actually a competition of better and better algorithms where the optimal algorithm is still not known and has not been found. So this is a syllabus of first chapter, motivating examples, and I suggest that we dive right into it by recalling the virtues of computer science. What is the difference? What is the difference between electrical engineering and computer science? I get often asked because both departments, both disciplines nowadays revolve around very similar topics and sometimes even on the same area. And students wonder, should I join computer science department or should I join the electrical engineering? What's the difference anyway? And the answer I give here is that the virtues are constituting computer science. So here you see a picture of Ada Lovelace, who is sometimes called the first programmer. And also you see here picture of the saints from the Bible, and all representing virtues, and the virtues of computer scientists to start with a problem specification, right? Before starting to solve a problem, before starting to devise algorithm for a problem, first make the problem unambiguously clear. And so one way of doing that is by giving a formal, maybe a logical specification, but that's just one of, it's not really necessary to do it so formally. The main point of here is to have it unambiguous. And because if there's any ambiguity in the problem specification, remember Murphy's law, what can be misunderstood will be misunderstood, and such a misunderstanding can have terrible consequences. For example, as you recall, the rocket launch, which went wrong because part of the rocket was designed according to the metric specification, but when building the rocket, people understood it to mean the to be in feet rather than in meter. And of course, the result was an unstable rocket, which in the end had to be destroyed. So be very clear, unambiguous. And if there's ambiguity also, that might result in, for example, legal repercussions. If you are a contractual programmer and you write a program, if you design an algorithm and then write a program, implement it, and it turns out that your boss, your supervisor, actually meant some different problem that from what you understood, then that ambiguity in problem specification may in the end up in court with serious financial repercussions. The next virtue of computer science is the formal semantics. That means to clarify which operations can you use when designing an algorithm and which are prohibited. That latter part is often omitted and again can result in misunderstanding and can have a drastic effect on the feasibility and efficiency of algorithms, as we will illustrate in this first chapter. So formal semantics, which is also essential later when we talk about rigorous verification, which builds on the formal semantics. Next step, third step, is the algorithm design, which I emphasize to be very different from programming and also different from heuristics. These are, in popular language, people easily confuse that. For example, they present algorithm for image recognition, but image recognition is not even a well-specified problem, right? What can be perceived as an image of a cupcake can also be an image of a ladybird, and there's many ambiguities. So we cannot speak really about algorithms for image recognition, and in many other cases like anyway, yeah. So that's the importance of algorithm design as opposed to programming, which is the process of implementing an algorithm, and which is also different from heuristics. Heuristics, which may be correct in many cases, arguably even in important or practically relevant, but for an algorithm, the whole deserves the term algorithm, it must be always correct, and it must be analyzed. Analysis here meaning the number of steps, the running time in some asymptotic notation like big O calculus, as opposed to absolute running time, physical time. Physical time can change if we proceed to, if we replace, for example, the hardware of a computer, or then maybe the same algorithm will run more quicker. But as we will demonstrate with examples, what really matters for an algorithm is the asymptotic cost, because eventually that will dominate and exceed any advantage that can be achieved by choosing a faster computer. So analysis with respect to efficiency, but also analysis with respect to correctness, because some of the algorithms were designed, for example, regarding approximation problems, we really need to make sure to guarantee a certain approximation ratio, approximation factor, and that aspect of correctness needs particular care and needs to be reflected as part of the algorithm's analysis, the fourth step. And the final fifth step, the fifth virtue, is proof of optimality. This is kind of the high art of complexity theory, proving algorithms optimal. I need to refer you for my parallel concurrent lecture, Theory of Computing, for a thorough introduction to that part with aspects such as NP completeness. But in the present introductory lecture on algorithms, we will usually get away with fairly superficial arguments why and whether an algorithm is optimal. And if the algorithm we have designed here and analyzed here and turn out to not be optimal, then the paradigm of algorithm engineering kicks in, and then that means we should start over from here and design another, hopefully better algorithm, analyze that better algorithm, and hopefully that will turn out as optimal. If not, go over it again. If it is optimal, then that's the good news. That's the purpose of this fifth virtue. Then it means we can stop looking for better algorithm because we can be sure to have finally found the optimal algorithm and thus settled that part of the problem. Okay, 5 virtues of computer science to be demonstrated now in the sequel of this chapter 1 of Introduction to Algorithms. So what's the importance of, why do I keep emphasizing the importance of specification? Because there can be ambiguities which by their inherent nature are not apparent to the person, to both participants in the communication, the one specifying the problem and the one designing an algorithm purportedly solving the problem specification. So it's very important to be as clear and unambiguous about the problem which we're considering before starting even designing algorithm. So problem specification. Right, let's look at some examples. First example, most instructive are as usually the non-example. So consider the specification, find me a girlfriend or boyfriend. This is not a problem specification for various reasons, which I'm not going to delve into further. What could be a suitable girlfriend-boyfriend material by one person would be discarded by the other. So it's really lack of specification, but that's only one of the problems, many problems with this assignment. So you will not see such an assignment in this course. Another specification is about the decision example, count example for a decision problem. The decision problem whether God exists, right? So is this a well-specified decision problem? I doubt it, because there's no consensus of what constitutes a correct solution to that problem. So that's another non-example of correct specification. Similar for many philosophical questions, how many angels can dance on the head of a pin, which is a popular question, but not an algorithmic problem specification. What is the best movie of all time? Also, opinions differ, and therefore this is not a good problem specification. How many print rights are there? This already starts to go into the realm of good problem specification, but this is less of an algorithmic problem. It's more like a problem in pure mathematics, which again exceeds the purpose of algorithmic approaches. The next example I'm particularly fond of, because it is a logical paradox, namely the question, is no the only correct answer to this question? This looks like a well-posed yes-no question, like a decision problem where the answer is yes or no. But on closer inspection, let's suppose first that yes is the answer. So that means a yes, no is the only correct answer to this question, which is a contradiction by itself. So that cannot be the case. Yes is not the only correct answer to this question, so it must be no. So that means no is not the only correct answer to this question, which implies that yes is also at least one correct answer to this question, which was just seen to not be the case either. So this is a logical paradox. Neither yes can be a correct answer, nor no can be a correct answer. So this is kind of a trick question which does not have any answer, in particular, no algorithmic solution. Okay, this is inspired by the undecidability of the halting problem and the, that I just taught about in the concurrent lecture in theory of computing. But moving on, similar paradoxes. What is the smallest positive integer that cannot be described in English using 100 characters? Again, superficially, this looks like a well-posed question and thus satisfy the virtue of specification. But if you look carefully, you see that whatever this smallest positive integer that cannot be described in English uses 100 characters, whatever that is, we have described it using 100 characters in English, meaning a contradiction. This cannot be the smallest. The smallest must be smaller than the one we have just conjectured. So this is another example of a question, of a trick question, which does not have an answer at all. Okay, so yes, admittedly, these are artificial or maybe just also merely intellectual examples, but they do demonstrate that specification is something to consider and to consider before starting the design of algorithms, and we'll look at more examples and non-examples and the importance of specification, arguably more relevant examples throughout the course of this lecture. Then the next virtue of computer science we emphasize to be the semantics. So that is demonstrated by some possible or arguable algorithmic solutions to the these example problems, namely meet your seat neighbor. Is that a suitable solution, algorithmic solution to the problem of finding a girlfriend, boyfriend? Well, certainly. Well, okay, I'm not going to go into further detail. Does God exist? Yes. Is yes an answer or not? Again, that's doubtful. What is a correct answer? How many angels? Try. And to find the best movie, here's a purported algorithmic solution to answer that question. I may simply start with the first movie ever, according, for example, to the movie database, and then look at all subsequent movies and compare every next movie to the previous one, whether it is a better movie or not. If it is a better movie, then record that and otherwise discard it. That algorithm should arguably result and produce the best movie of all time, right? So this is a simple adaptation to the standard linear search for maximum element in an array that you all are aware of course, adapted to the problem of finding the best movie. But does that really identify the best movie? And if not, where's the problem in this algorithm? It looks like an algorithm, right? And it every single operation seems reasonable and seems to provide in the end the best movie of all time. But also everybody would agree that the question, what is the best movie of all time, is not a well-specified question. So there must be some error in this movie, in this algorithm, and ask you to find where in this algorithm is the mistake. Yet. Okay, moving on. Third virtue, algorithm design as opposed to programming. And here I'd like to give a short historical anecdote from my life. When I was young, I would switch from high-level programming language to assembly code in order to fully harness the computational capabilities of my, at that time, still very slow computer. Direct assembly coding And I did, and I wrote what I believed to be the fastest possible sorting algorithm for sorting, let's say, integers. And here you see it. You see the fastest sorting program for integers, hand optimized every single CPU cycle of every single CPU instruction here, counted for in the separate table, including all the overhead for branches taken or not breaking. But when I started taking computer science courses myself, I realized that this implementation, highly optimized, hand-tuned, was an implementation of bubble sort. And of course, we all know bubble sort is a quadratic time algorithm, whereas asymptotically much more efficient algorithms with running time n log n are known. And so I spent all my efforts writing fast programs, but among all the trees and among all the optimization attempts, I missed and I failed to see the big picture, and the big picture being provided by the abstract view, by the algorithmic view, as opposed to the local confusing picture of programming. So this is to emphasize the difference and the importance of devising algorithms as opposed to writing programs. Or as Donald Knuth said, premature optimization is the root of all evil, and I fell for that evil. I did premature optimization. So the right way, the right order is to first devise the asymptotically most efficient algorithm, devise, analyze, prove optimal, and then to start optimizing on lower levels, such as maybe or maybe not even nowadays on the assembly code level. So another example to illustrate possible pitfalls of what is not an algorithm. Here we consider the problem of sorting vowels. So here you see a list of 5 vowels, and how do you sort the vowels? In this example, we invoke the sorting subroutine and then output those vowels. So this is a very superficially very efficient algorithm because it only contains 3 instructions. Here that's the initialization that may not even count, then making 1 sorting operation, and then we're done. But you see, as this algorithm is cheating, right? Because it is hiding all the actual effort, the workload of the sorting in this 4 symbols SORT, without telling how to do this actually, right? So the point here being, if sort is among the permitted primitives, then it just takes 1 operation, namely a call to this primitive, to sort. But if sort is not among the primitives, or if we are actually asked to implement, to realize that primitives based on lower level instruction, then this is not an algorithm. This is a biting its own tail, right? Realizing a sorting primitive by using a sorting primitive is not a solution. So the difference is algorithm versus code in the first example, and the importance of which primitive operations are permitted and which are not in the second example. Also important is the semantics. For example, in the code here uses machine integers, which are, as you know, different from mathematical integers. These have a fixed length, fixed width of, let's say, 32 bits. And after 32 bits, there comes a wraparound, which does not occur in mathematical integers. So the semantics of, for example, the increment operation is different, whether it applies to machine integers or to mathematical integers. And confusing that semantics can lead to serious programming errors that will maybe illustrate also in a second. The next thing to consider is the cost of these primitive operations. namely, like for example, let's consider the multiplication primitive. Multiplying two integers must be boiled down to applying several multiplications on machine integers if the integer is very long. So counting one multiplication as one step may be accurate if the data is small, but maybe give an inaccurate prediction of the actual program's performance when the data under consideration is very large. So simply counting the number of operations can give a misestimate, underestimate of the actual performance, but that's the whole purpose, and that it thus violates the whole purpose of analyzing the computational cost of an algorithm. Then the purpose is to give an estimate and prediction of its actual real-world performance without actually having to run it, and also a prediction which does not depend on hardware details that change with every new model, but an algorithm should be and is an entity of its own, and its computational cost is also something that transcends and goes beyond the actual details. So abstraction is really the key here, as well as in, for example, data abstraction in object-oriented programming or in mathematics abstraction using high-level operations with specified semantics and with specified costs in order to design algorithms and then implement them or have them implemented by a compiler, and hopefully then the predicted performance agrees with the actual performance. And in order to design and present algorithms, we will use various ways, right? So we won't present algorithms in assembly code for obvious reasons that I've just demonstrated. Or one way is using pseudocode, but pseudocode is only one of several approaches, because as I kept emphasizing, an algorithm is by itself, by its nature, an abstract object, and that can be described and will be described in various ways, not always by pseudocode. So here you see, to illustrate the point, here you see a pseudocode of a bubble sort algorithm, which I happened and only later realized to be have implemented in machine code. Yeah, because I succumbed to the failure indicated by Donald Knuth of premature optimization. And you see here already illustrated that this pseudocode, this pseudocode uses various primitive operations such as comparison here, assignment, for loop, another comparison if then, and swap. And for each of these operations in the analysis of this algorithm, we need to take into account the computational cost. So a popular way of analyzing bubble sort, maybe arguably even a standard way, is to really just count the number of operations. But as I emphasized, one comparison or one swap operation or one assignment may or may not really be accurately charged for with one unit cost as operation, but it may depend on the size of the data involved, right? So if this, the content, the data to be sorted consists of just bytes or words, then it's fair to say that one swap operation takes one step. But if the data to be sorted involves very long integers, 1000-bit lengths, 10,000 bits, then really swapping two of these large data must and will, of course, be broken down into many single byte swapping operations. But the number of these single byte operations depends on the magnitude and value of the data. So larger data will have more cost and therefore more accurate analysis will take into account also the magnitude of the data on top of just the number of operations in order to get a better prediction of the actual practical performance when and after implementing that and running that on actual hardware when turning the abstract algorithm into a real-world program executable. Right. So let's look at more closely at the relevance and influence of the data size at the example problem, which we'll look at more closely later, namely the problem of multiplying two integers. And here the emphasis is already on integers of variable and maybe even very large length, right? So let's first try something like long multiplication, which you definitely know, for example, from high school, which can be considered as decomposing one of the two arguments, one of the two integers to be multiplied into their binary representation. Well, in school, you certainly have learned it decimal representation, but here it's binary representation. And then adding up copies, shifted copies of the other integer here, a, shifted copies, several of them, and adding up those corresponding to binary digits 1 here, and omitting those corresponding to binary digits 0 here. And the position of the binary digits 1 here corresponds to the amount of shift of the other argument here, so that after adding, right, so if this is 0, then do not add this one. If this is 1, then include this shifted copy, and so on. And then adding all up. Thus, the multiplication of two n-bit integers can be expressed by an algorithm, can be solved by an algorithm using n additions. So this example demonstrates very nicely several aspects that I've been emphasizing before. First, which primitives are permitted, right? So if multiplication is a permitted primitive, then there's no point in writing a multiplication algorithm, designing and analyzing a multiplication algorithm, because multiplication itself is already permitted. If multiplication is not permitted, but if addition is permitted, then this algorithm allows to express, implement, and realize multiplication of n-bit integers as a series, as a sequence of n additions and shift operations, which are used here implicitly, so that the computational cost of this algorithm is linear O of n additions. And also observe that this algorithm I'm presenting, well, it's all trivial, right? But from the algorithmic perspective, but the emphasis here is that this algorithm here is presented not as pseudocode, right? You can easily turn this algorithm into pseudocode. I leave that to you, but this is an alternative way of presenting an algorithm for multiplying two n-bit integers by means of n additions, a linear cost algorithm without pseudocode. And the third thing that this example illustrates is algorithmic cost. So here we count just the number of additions and implicitly assume that every addition takes one step, is charged 1 unit cost. This is an implicit hypothesis here in the algorithm analysis, which may or may not be true in actual practice. So that's why it's important to emphasize the cost. Namely, in actual practice, adding two n-bit integers itself may take up to n steps, right? Adding two n-bit integers, if that has to be boiled down further, right? So the next step is to design an algorithm for adding n-bit integers. And adding n-bit integers, if the unpermitted primitive is addition, is again trivial. If the permitted primitive are just basic Boolean operations on bits, then adding two n-bit integers costs linear cost in turn, resulting in this computational cost to increase to n squared, so that this algorithm, implicit algorithm, suddenly becomes a quadratic time algorithm, right? So here you see the shifted copies and the additions in this more closer and therefore more realistic perspective means that each addition involves two n bits each, right? N bits here, but after the shifting of at most n bit, this all fit into two n bits, and each addition of two n bit each has linear cost, so that the overall cost, the bit cost of this non-pseudocode algorithm becomes quadratic. Let me emphasize that again. In the first round, we analyzed only the number of operations, discarding the effect of the size of the data. In the second round of analysis, we counted the number of bit operations, which gives a better prediction, but a more involved analysis of the actual performance, which turned out to be quadratic and raises the question, can we multiply two n-bit integers with less than quadratic number of bit operations? Okay, I hope that makes sense. And this is all the example of the semantics and costs and primitive operations. If addition is permitted, if we agree in the problem specification that addition is permitted as a primitive operation with unit cost, then this is a final answer. And this can be shown to be the optimal algorithm. N additions is optimal for multiplication. But if addition is not among the permitted primitives in the problem specification, or if addition is permitted but with non-unit costs instead with linear cost, then this non-pseudocode algorithm results in a quadratic bit cost, which is not optimal, as we will see in a minute. So this is to illustrate the importance of agreeing in advance which operations, primitive operations, we can use in composing and combining to achieve the algorithmic goal according to the specification, first virtue, and what is the semantics of these operations, and what is the cost of each of these operations, because each of these will determine what is the cost and what is the optimal cost of an algorithm for solving that problem. So yes, as I said, on the bit cost level, quadratic cost as attained by this example algorithm is namely not optimal, and because very recently Harvey and van der Hoeven have succeeded in devising an algorithm that can multiply two n-bit integers using only n log n bit operation. And this algorithm is very, very sophisticated, and also its analysis is an entire problem of its own. But this is really, I emphasize this also because this is the world record on this field. So kudos to Harvey and Joris van der Hoeven. Actually, I think it's over 50 years sequence of better and better algorithms for that problem, and they have attained the current world record. Okay, so long story short, algorithm design is a very interesting area, both intellectually and practically relevant. It's very different from programming. It precedes programming, and the algorithm analysis is also a very involved matter. There are actually entire books called about algorithm analysis, and there's a CS300 course that also I occasionally offer, that is called Design and Analysis of Algorithms, with the emphasis on analysis, various ways of analyzing algorithms beyond the worst case paradigm that we restrict to, however, in this introductory course, CS300. So, right, and when we talk about algorithm analysis, one aspect is correctness and the other aspect is algorithmic cost, with emphasis on asymptotic cost. Why is asymptotic cost so important? Because that's what really determines the practical efficiency in the long run. So let me illustrate that with a table. In this table, you see 5 columns corresponding to 5 computers, some hypothetical, some real, of different operational speeds. So the first column refers to a computer which may seem very slow because it can only make one operation every 10 seconds, just as a thought experiment. The next computer takes about 1 second for each operation. This is getting close to, for example, the SUSE Z3 computer, which would do about 10 operations per second using mechanical switches. The next computer makes 1,000 operations per second. So every operation, hypothetical computer, every operation takes about 1 millisecond. The next computer makes 1 billion 1 million operations per second. This is, imagine this to be the early Apple IIe computer or the Commodore 64 computer. They had such a clock frequency, 1 million operations per second. And this is a representative of our current state of the art gigahertz computer. Actually, let me point out that after Moore's law, which predicted that the size and the performance of computers would double roughly every 2 years, has long been discarded. And so over the past 10 or 20 years, the clock frequency of computer hasn't really updated very much. So gigahertz is still state of the art. And what we consider here are these hypothetical or real computers with different clock frequencies ranging from very slow to very fast. What you also can see here is in each column refers to a hypothetical algorithm run on this computer with different asymptotic cost, right? Cost as opposed to runtime. This one algorithm, hypothetical algorithm, has logarithmic cost. This one has cost n log n, as for example, the world record of integer multiplication that we just discussed before. This hypothetical algorithm has quadratic cost, such as, for example, the naive or the long multiplication. This one has cubic cost, such as, for example, naive matrix multiplication is a typical cubic cost algorithm. And this one has exponential cost asymptotically, such as common Boolean satisfiability problems have exponential cost. So to summarize, what we're doing here is we're taking a very, very slow computer, but executing it on a thought experiment, an asymptotically highly efficient logarithmic time algorithm. And on the other hand, we have a faster state-of-the-art computer in terms of its performance, but we execute on it very demanding exponential time asymptotically algorithm. And on this trade-off between, we have various stages, faster algorithm with less efficient computers and vice versa. And the question is, in a hypothetical race, which of these pairs will win? The fastest computer with the slowest algorithm or the fastest algorithm with the slowest computer? And as you can see here, initially, it's really the performance of the computer that dominates. For small inputs, the fastest computer dominate and win. But as soon as the size of the problem grows asymptotically, the faster algorithm immediately start to take over from the fast computers. And already here, the seemingly slowest computer is actually outperforming all others, well, except for this one. But as the input size grows further, in the end, it's really the fastest algorithm that have the strongest impact, and the performance of the computer becomes negligible. And already here, for example, the exponential time algorithm will never even terminate on inputs of size 100, whereas the fastest algorithm on the slowest computer just takes 1 minute. Just for reference, recall that the age of the universe is roughly 13, 14 billion years, and 40 billion years is far beyond that. So the emphasis, the lesson, the point I'd like to make here is emphasize on algorithm analysis, and don't worry about actual empirical program evaluation. Absolute running times do not matter at this initial stage. And again, paraphrasing Donald Knuth, premature optimization is the root of all evil. Do start optimizing only after you have devised and analyzed and proven the optimal algorithm. So that's a message to take away here. And to recall some mathematical background from discrete mathematics, some classes, far from exhaustive, some classes of asymptotic growth are illustrated here using the Landau or big O notation. F grows asymptotically as fast as G, and I refrain from spelling out the mathematical details, but just provide the intuition with this picture. So here are two asymptotic functions, f and g, depending on a parameter k. And as k tends to infinity, that means a focus and emphasis on asymptotics. Initially, the first function f dominates the second one. So an algorithm here would be slow, and this algorithm would be fast. But as the input size, which is denoted by k here, as that grows, actually both become comparable. They differ only by a constant factor. And one of the benefits of the big O notation is that constant factors and constant offset can be ignored, and thus allows to drastically often simplify the expressions and make the expressions transparent and allow to compare algorithm, right? So imagine, for example, one algorithm that takes 5 minutes on one problem and 2 minutes on another problem, and another algorithm that takes 10 minutes on one problem and 1 minute on the other. Which one would be better? You cannot really compare the two algorithms. They cannot be compared because in some cases, the first algorithm is faster. In other cases, the second algorithm is faster. But in this example, they're only faster by a constant factor, whereas in asymptotic notation, as asymptotic analysis, one can rigorously compare algorithms asymptotically. And here's some illustrations and examples of classes of asymptotic growth, starting with constant asymptotic growth via logarithmic asymptotic growth. Remember, that was our first column in the previous table. Square asymptotic growth, linear growth, quasi-linear growth is often means n log n, like the world record integer multiplication algorithm. Quadratic asymptotic growth, cubic, polynomial means n raised to some constant. So that generalizes all the previous one and includes and exceeds them. And also we ignore constant factors and constant offset. And then super polynomial, right? And then come exponential. This is good opportunity to emphasize that these examples are far from exhaustive. Between any two of these classes, there's always some intermediate class, which may or may not actually occur in practice and may or may not be exhibited by example algorithm. So between polynomial and exponential, there is some class of asymptotic growth in between. And then beyond that, there's double exponential. And then there's a tetration operation, which is exponentially to a tower whose height depends on the parameter n. So this is really, really bad asymptotic growth. But as I kept emphasizing, these classes really occur. And more precisely, to each such class of asymptotic growth, there's an inverse, right? So the inverse of exponential growth is logarithmic growth. The inverse to doubly exponential is doubly logarithmic. So we will talk about these classes of very fast and very slow asymptotic growth later, up to, for example, the famous inverse Ackermann function that governs the running time of the union find algorithm. Okay, so here's graphical illustrations of these classes of asymptotic growth. And what is new here is the factorial, which according to Stirling's formula grows essentially like e to the n log n. So depending on how closely we look at the exponent, this grows as fast or strictly faster than exponential. Good, so asymptotic growth as part of the virtues of computer science in part of the analysis part of the algorithmic cost. The other analysis part, as you recall, is concerned with correctness of the algorithm. And finally, the last virtue, the fifth virtue, is that of algorithmic optimality, which we'll discuss in a minute. But first, let me also introduce some notation and clarify some common pitfalls of misunderstanding. Namely, when we talk about asymptotic growth, usually we use a parameter n to describe the quantity that is growing asymptotically. And that quantity n often denotes the binary length, which needs to be carefully distinguished from the binary value. And that's a common source of misunderstanding. So I really want and need to address that and emphasize the difference. So to illustrate that, compare writing this number 2 to the 999 in binary versus in unary. Well, in binary, this number is a 1, digit 1, followed by 999 digits of 0. So that the binary length of writing this is a huge number, right? But it can be written in binary using only 1,000 binary digits. 1,000 binary digits, that's doable as part of a whatever homework assignment or so, right? You can do that. It's not my favorite activity, but writing down 1,000 digits can be done in a reasonable time, as opposed to writing this number in unary. Right? Writing this number in unary means writing some unary symbol 2 to the 999 times. And that cannot be done ever, right? So that takes running time far beyond the age of the universe. So writing this number in unary is infeasible. Writing it in binary is feasible. And generally speaking, writing an integer or natural number in binary takes a length which is roughly logarithm to base 2 of that number. So now very concisely, whereas writing it in unary requires a length which is roughly equal to the value. So here's the length is logarithm of the value, and here's the value itself. And you can imagine that this is a huge difference. And that difference is also reflected when we analyze algorithms independent on either the binary length or the unary length, which is synonymous with the value. And a popular example where this confusion occurs is, for example, integer factoring. So, or let's consider more primitively the question whether a given natural number is a prime number or not, right? So there's a ancient algorithm, sieve of Eratosthenes, that tests whether a number is prime by canceling out all multiples of numbers which we already have considered. Here we consider an analysis of this algorithm and observe that this algorithm can stop after roughly square root of n having reached the square root of n, because if n does not have a proper factor smaller than its square root, then it cannot have a proper factor larger than its square root as well, right? Because to every proper factor, there's a cofactor, and if one is smaller than square root of n, then the rest is larger and vice versa. So that superficially, the sieve of Eratosthenes looks like it is a polynomial time algorithm, right? Square root of n is even better than polynomial, right? It's even sublinear. But here we have analyzed and stated the computational cost of the sieve of Eratosthenes in terms of the value, that is, of the unary length of the argument. Whereas the common way of analyzing algorithms depends on the binary length, that is logarithmic in the value, and that was not known to be possible for the testing primality until 2002, when AKS devised an algorithm whose running time is roughly later, and an improved analysis turned out to be roughly logarithm to the 6th of the argument n. And yeah, let me emphasize that again, this does not mean logarithmic running time. This means polynomial running time, but polynomial in the binary length, namely or the 6th polynomial in the binary length, which is roughly the logarithm value. So that's a polynomial time algorithm. It's a very difficult actually to prove correctness of that algorithm. That was maybe a key issue in the breakthrough, and then analyzing the bit cost of that algorithm, as opposed to this long-known algorithm, sieve of Eratosthenes, whose running time is not polynomial in the binary length, not polynomial in the logarithmic value, but only polynomial in the unary length, that is in the value. So please refrain from, don't fall for this very popular and common confusion, and also try to educate your environment when you graduate. After you've graduated, you're a kind of a multiplier to eradicate, to purge this common misunderstanding. And the same difference applies to factoring integers, only until nowadays there is not known to be any polynomial time algorithm polynomial in the binary length, that is no polylogarithmic algorithm in the value. And this algorithm not to be known is actually the key to common cryptographic schemes that like online banking nowadays are based on. Or put differently, if you by any means happen to find or devise and analyze an algorithm that can factor integers in polynomial time in its binary length, then you're either famous or sought after, because that will immediately topping all the bank systems throughout the world, because they're all connected and use the same or similar cryptographic schemes. So this is the basis of the famous RSA crypto system. So there's a separate lecture on cryptography that I'm happy to cross-promote and refer you to. Okay, so long story short, don't confuse binary length as a complexity parameter from unary length, which is the same as value as complexity parameter. But that being said, we often do identify the binary length with a number of elements for reasons that will become apparent later. For example, when multiplying polynomials, we count the degree, that is the number of coefficients, or when multiplying matrices, we count the format of the matrix as complexity parameter, but that's later. Right, and now finally turning to the last and fifth virtue of computer science, proving an algorithm optimal. So after having completed and performed all these 4 steps, first on problem specification, then clarifying the range of operations, their semantics and their individual algorithmic cost, then third step, devising an algorithm, and fourth, analyzing both the correctness and the computational cost incurred by this algorithm. Then we wonder whether we have finally found the optimal algorithm, or if not, whether we have to start over again and design a new and hopefully better algorithm. And as I emphasize, this is really the high art of complexity theory, which we will not touch in this lecture, which again, I'm happy to cross-promote you to theory of computing. There are some simple examples that we use here in the introductory section 1 to illustrate the question of optimality with some example problems. The first problem we consider is the powering problem. For this, we fix some monoid. Now, for those of you who are not hardcore mathematicians, don't worry about this terminology. Monoid is just something where we can, where one can perform multiplication. Examples being, for example, natural numbers can be multiplied, matrices can be multiplied, polynomials can be multiplied. And here we consider the problem, and this is the first example of problem specification. Given some element x from that matroid, imagine that to be an integer or a matrix or polynomial, and given a parameter n, and the goal is to calculate in output x raised to the nth power, which is abbreviation for x multiplied to itself n times, right? So multiplication being the operation supported by this monoid. And yeah, following through with our emphasis on full problem specification and full specification of the operational primitives, we want here to count as cost the number of multiplications, regardless of whether this is realistic or not. And actually also in your homework and midterm and other exam assignments, we will always make clear or ask you to make clear what is the computational cost you charge and which are the primitives you use. So there will not be any ambiguity. This is a common question raised by students of this lecture. Can we suppose this or can we not? And the answer is, if you want to suppose this, just say you suppose it, unless we have specified in the assignment what or not you should not suppose. So anyway, so this is a kind of strictly according to the rule book problem specification here, and specifying the semantics and the computational cost of the primitives. And here you see a first algorithm again beyond pseudocode, namely an implicit algorithm, which I can paraphrase as just multiply x to itself n-1 times, n-1 times, because the first one doesn't need to be multiplied, right? There's nothing to do in the first case. But asymptotically, that doesn't make much of a difference, right? This is a linear number of multiplication, so this is linear cost. And the question is that optimal or can we do better? That's the gist of the fifth virtue, algorithmic optimality. Here we have, which was trivial to be honest, designed and analyzed that algorithm. And now the question is, are we done? Can we go home, or do we need to start over and look for an asymptotically better algorithm, right? Asymptotically, this plus minus 1 doesn't really matter. If it's n-1 or n, we don't care. And how can we answer that question? Well, by trying to devise a better algorithm. And here is such an example, and it happens to be a recursive algorithm. Namely, multiply or obtain x to the n recursively by first solving a problem of half the size, right? Divide and conquer, raising x to the n over 2. Here we suppose that n is even. And then squaring that is multiplying the result, the intermediate result to itself. Multiplying to itself, that's one multiplication. In the case that n is odd, this is not an even, this is not a number. So in this case, we raise x to the power n-1 over 2, which happens to be an integer, then square that intermediate result, multiply to itself, and then multiply another x to get the result. And this immediately analyzing that algorithm leads to the following recurrence on its computational cost, recurrence on the number of multiplication. So for raising x to the first power, we don't need to do anything. That's the initial condition. And in general, raising x to the n power can be done by raising x to the power n over 2, rounded down if x is odd, right? Then squaring, that is multiplying it by itself, that's one multiplication. And possibly another second multiplication that you see here in case x is odd. So in both cases, this is less or equal to this quantity. And now solving that recurrence, right here, see it spelled out in both cases separately. In either case, it's less or equal. So thus solving that, for example, induction shows that the computational cost, the number of multiplications incurred here, is at most 2 times the binary logarithm of n, which means this is a logarithmic time algorithm as opposed to the linear time algorithm that we saw here. And so we have indeed now devised an asymptotically superior algorithm, very fast. Remember, logarithmic was the algorithm that beat all other computers in our hypothetical table. And it also answers the question whether our first naive algorithm was optimal. It was not, far from. So, but now we're back to a square one, right? Better algorithm. Is this an optimal algorithm or not? If it's not, we have to start devising a better algorithm. But what can actually prove that that this is asymptotically optimal, that a logarithmic number of multiplications is required, is necessary in order to solve this powering problem. And this proof, which we'll give to wrap up today's lecture, is it uses mathematics, uses the mathematical concept of a degree. So this is our last slide for today. So we have just devised and analyzed a better algorithm which uses at most 2 times log algorithm, and one can prove, and we will prove that actually later, that first statement, any algorithm that starts with input x and uses only multiplications, no other algorithm operations, produces only monomials as intermediate results. It's kind of easy to see if you know what monomials are from discrete mathematics, cannot produce anything else. And that can be proved immediately by induction on the number of steps performed by the algorithm. So I won't do that in detail. The second claim of the lemma is, after having executed L multiplications, all intermediate results, which we know to be monomials by item A, have degree at most 2 to the L. We cannot get a higher degree than 2 to the L using L multiplications. Again, this statement can easily be proven by induction on the number of multiplications used, so I won't spell it out. And putting these things together in order thus to produce among the intermediate results, the final result which is required to have degree n, right? This is degree n. That means, taking the logarithm on both sides here, that means L must be at least the logarithm of n, binary logarithm. And that's our statement. Any algorithm computing x to the n requires at least log n multiplications if no other operations are permitted. And our algorithm, which we just designed using this divide and conquer recursive approach, achieves that up to a factor of 2 and therefore is asymptotically optimal. We are done. We have found the asymptotically optimal algorithm only if we really want to look more closely and now start optimizing according to Knus. This factor of 2 is present here, is absent here. Can we get away with it? And that's a starting point of a much more involved and long research question, which goes far beyond the present lecture, which I want to conclude now with a brief summary. So we've talked about the 5 virtues of computer science: problem specification, semantics of the operations involved and computational cost of each operation, algorithm design and analysis regarding correctness and computational cost as opposed to program. And fifth virtue is proving algorithm correct. And we've illustrated all these virtues with examples and with non-examples, some more on the silly side and some more reasonable. And we've also illustrated the algorithm engineering paradigm of devising and analyzing an algorithm and either try to prove it optimal, or if it's not, then start over again and devise a better algorithm, analyze it, correctness and computational cost, and prove that optimal. And once we've found an asymptotically optimal algorithm, then we're done. And then we can, and maybe even should, start to look more closely beyond the algorithm asymptotic perspective, looking for constant factors. According to Donald Knuth, premature optimization is the root of all evil. So that's all for today. That's all for the first lecture. Thank you very much for your attention and see you again next time.